So before we go further with this section of the assignment, where what's going to happen next is you're going to be asked to calculate a 95% confidence interval. But before we get into that, I want to just recap on a few concepts. So we're looking here at a symmetrical distribution. And so a normal distribution is a type of symmetrical distribution, but a normal distribution actually has a very specific definition in that it also has a mean of 0 and a standard deviation of 1. So even though many times when we say something is normally distributed, what we usually mean by that is we mean it's actually symmetrically distributed, meaning that, if this is the middle of the distribution, then this side and this side sort of looks the same. If you imagine folding it in on itself, then the two sides are similar. So they're symmetrical. But when you actually want to be completely correct, if you're going to talk about a normal distribution, then that's actually a distribution that has a mean of 0 and a standard deviation of 1. So I'm just pointing that out. So what we're looking at here is a symmetrical distribution that has the sort of the shape of a normal distribution. And why I'm showing you this is because this explains the concept of what we're doing when we are using resampling statistics to calculate a confidence interval. So in any distribution like this, we can calculate what we call the area under the curve. And doing that calculation has a very specific role in terms of probability. And so statistics is all about probability. If you remember from your lectures on the permutation test, the question is usually, what is the probability of getting a result equal to or more extreme than the result you got? And so that phrasing is very important because it kind of focuses our attention on the fact that we're talking about probabilities here. So if you look at this distribution and you think of it in terms of probability, then if this is the median, this yellowish line, which it is, I plotted the median on the plot. I calculated the median and I put a line there where the median is. Then the definition of the median, if you remember, is that 50% of the values are below that value, or conversely 50% of the values are above that value. So another way of saying that is that the probability of a value being here on this side of the median in this gray area is 50%, because 50% of the values are below the median. So any value, if we draw from a bag any one value, then that value has a 50% chance to be on this side of the line of the median, and it also has a 50% chance to be on this side of the median. And so exactly the same way as we could calculate a median, and in that case the probability is 50% or 0.5, we can obviously also draw other lines on this plot that has other probabilities. And that's what these lines are. So this red line and this red line, as you can see there, I typed the probability. It says 0.025 in this case. And in this case, it says 0.975. And so in the same way, where this line represented a probability of 0.5 for any value that is in our data to fall below or on this side, in this gray area, in the same way we can calculate the area of this gray area, which is obviously much smaller, but we can calculate the probability that a value lies in this area. And that, we don't have to calculate it, that's what the line is. That's what the definition this line is. This is the 2.5th percentile. So 2.5% of values are below this line in this gray area. And so if I draw any value that is in my sample from the bag, the probability that that value actually falls inside this area is 2.5%. In the same way that the probability that that same value falls in this whole gray area, that probability is 50%. The probability that it falls in this very small area is 2.5%, because that's the definition of this line. I worked out the 2.5th percentile, and that's where I drew this line. So for any distribution, you can work out, there are functions, and that's the function you are going to use in our exercise just now. You're going to use the quantile function. And so you use the quantile function to find these values. For any distribution, you can find the value where, if you said, I want the 30th percentile, you can find a value somewhere here where if you draw a line, then the chance that the probability that any value falls below that line and in this gray area is 30%, or 0.3. So that is the principle we're using when we are using resampling statistics to calculate a 95% confidence interval, for example. And so remember, you'll get used to people saying 95% confidence interval, but it doesn't have to be 95%. You can also calculate a 90% confidence interval. You can calculate an 80% confidence interval. And you do that in different situations. It's just that the 95% confidence interval is the one that's mostly being used. So that's what you are going to calculate as well. But so the principle is this, basically. We can find the place on this x-axis where the chance, the probability that any value falls in this little area is 2.5%. What we're trying to say with our confidence interval, and don't quote me on this, because the confidence interval, the formal definition of it is a confusing thing. If it's still weight we're talking about, so remember we have a sample, we measured their weights, and we know what the mean weight in our sample is. So we don't need a 95% confidence interval for our sample because we measured all of them. We already know what their weights are. So we don't need to give some measure of uncertainty, because we are absolutely certain about what the weights in our sample is, because we measured all 400 of them, we weighed them. And so we know what their weights are, and we know what the true mean weight of our sample is. Our problem and our bigger question is, what does that say about the whole population we care about? And that's where we use a 95% confidence interval. Because as everyone can appreciate, the mean weight in the whole population that we care about is not going to be exactly the same as the mean weight we found in our sample. So what we do with a 95% confidence interval is to try to give a range, to say this is a range, and we think that the true population mean must be somewhere in this range of our 95% confidence interval. So that's the concept, that's how you interpret it. That is not the formal definition. And Gian will give you the formal definition in the lecture. It's not easy to explain and to wrap your head around, But don't worry so very much about the formal definition of the 95% confidence interval. The broad concept that you should have in your head is that we give a 95% confidence interval because we're trying to estimate how uncertain really we are about the weight. And so how you interpret 95% confidence intervals, if you have quite a narrow one, then that means that, that's good, what we call precision. So it means we're not massively uncertain about what we think the true population weight really is. Whereas if you have a very wide 95% confidence interval, then it could be almost anything. So it means our experiment didn't really contribute to knowledge around the question, because if our 95% confidence interval for weight ranges from 45 to 120, then that means, well, the mean of the population can be almost anything. And so that's really not helpful, because I can tell you that the mean population weight will be between 45 and 120. I can tell you that without doing an experiment. I don't have to spend any money on any experiment to tell you, well, it's probably between those two values. I can tell you that just from my life experience. But if I really want a precise estimate, and I actually go out and do an experiment, then I should design my experiment in such a way that I come up with a much narrower confidence interval. So for something like weight, I would expect to have at least, it shouldn't be wider than, let's say, 5 to 10 kilograms on either side, because otherwise there was no point in doing the experiment if I can just guess as well. So that's how you interpret a confidence interval, and that's why we are doing this. So when we have this plot, and we use 2.5% on this side and 97.5% on this side. And why 97.5%? If you remember that this whole area, so the whole gray area that we see, so remember I spoke about area under the curve, that's what we call it. The area under the curve of this whole, so the curve is the, where a curve would be if this wasn't a histogram and we just smoothed it out. The whole area under the curve, by definition, is equal to 1. So, or 100%. So if I want 2.5% of an area under the curve, that is equal to 1, the whole thing. If I want just this part, then that's 2.5% on this side. And on this side, I need the percentile that corresponds to 97.5%, right? Because if I take 1 minus 0.025, then I get 0.975. Okay, so we call these the tails. So this is the lower tail and the upper tail, or the left and the right tail. So this tail is 2.5%, this tail is 2.5%, because we're working out, in this specific case, the 95% confidence interval, right? So we want to know where the outer 5% of the data is, below which value and above which value. So we split the 5% in two, basically. And we work out which value over here on the x-axis, if any value is below that, it means it's in the lower 2.5%, and over here, whatever this value is that corresponds to this 0.975, anything above that value is then in the upper 2.5% of the range of this variable. But so now we should bring it all back to the sampling distribution that we calculated in the previous session, when you took the 1,000 samples of 400, the resampling that we did, And we created a histogram that looked a lot like this one, except it had different values on the x-axis. So when we're going to calculate our 95% confidence interval, we are not going to use the distribution of our sample. When we were doing the resampling and we created this plot, remember we said if this was a plot of just my sample of 400 and all of their weights, then over year 67 this would represent just the individuals in my sample that had a weight of 67. But now that we did the resampling, this whole distribution is not of individuals, but each like this 67 in this case, it represents all the samples of 400 of those different resamples that we took. It represents all those samples that had a mean of 67. So this distribution is a distribution of means. And if I took the mean of this distribution here somewhere in the middle, that would be the mean of means, right? So that's a concept to wrap your head around, but it's a concept we use when we want to calculate the 95% confidence interval. So this whole story that I told about the other distribution that we had, the distribution I just showed you with the orange and the red lines, where I was explaining we're basically finding the place on the graph where 2.5% of the values are lower than that line or more extreme. Remember, those are important words. Or on the other side, on the right side, in this tail, if we had a line here and we knew, okay, 2.5% of values are larger than this value or more extreme. So that principle we're going to use not on our one sample of 400 that we started with, but we're going to use that principle on this distribution, this sampling distribution, which is a distribution of means. It's not the individuals anymore, it's a distribution of the means of all those 1,000 samples that we took. And it's on this distribution that we are going to work out which value on this x-axis, let's say it is 67, let's say that's the answer we find, that below 67 there's 2.5% of the data. And let's say here above 69.5 or something, there's 2.5% of the data. And so then basically what our confidence interval is saying, if just theoretically those are the values, let's say it's 67 and 69 in this case, what we are then saying is that we think that the true population mean probably lies somewhere between those two values. And again, that is not the formal definition. So you have to try to wrap your head around this formal definition, because I think you have to know it for the exam. But the concept is that we're trying to measure how uncertain we are about where exactly the true population mean might lie. And that's why we're going through this whole exercise, because we're trying to say, we think, we're trying to define a range, sort of, where we think the true population mean lies, given that we have calculated to the best of our ability all of these means from 1,000 samples we got by bootstrapping or resampling with replacement. And so now you're going to go ahead with the exercise. So I ask some of the questions I ask here, I just answered in the video, so you shouldn't struggle too much. Over here you're going to write your own code. And so give it a try. And then here in question 6, I tell you to write pseudocode. Write pseudocode. So what is pseudocode? So I'm going to demonstrate it. Don't worry about that. So let's say we're in R and I created a table or a data frame as you've been doing before. Don't worry about this code. Looks a bit intense, but don't worry about it. I'm basically just creating two columns, and if I run it, you'll see that that's what I did. I created a and a B column. And now I ask you, what is the difference in the means of A and B? So what's the difference between these two columns? So if I was just going to write R code, because we're using R, this would be the syntax. That's what we call syntax. It's the actual code, the form of the actual code, which words and brackets and things you're using. That's the syntax. So this would be the syntax to answer this question. I do this. I assign to the object A the mean of example $A. Do the same for B, and then I say A minus B. Okay, so I run that and I get an answer. So that's the actual code. But what I mean with pseudocode is we're not going to use the actual R code. We're not going to use the syntax of the actual R code, but we're going to write down the steps that we would follow in any coding language. So it's a way to write, it's as if you're writing code, but you're just using normal words. You're not using the syntax of any specific coding language. There are many coding languages. R is one, there's Python, there's Perl, there's all sorts of coding languages. So the things we're doing here, we can do in any of a number of coding languages. We just happen to be using R. So writing pseudocode is writing the steps that you would follow in any coding language, not a specific coding language. So in this case, if I had to answer what is the difference in the means of A and B, I would think which steps would I use. So here I already have the steps, but now in pseudocode I would write maybe step 1, calculate the mean of column A. Okay, because that's step 1, that's what I did here. So don't write the code. So I'm going to delete that code because I covered it in my pseudocode. Then step 2 is the same thing. It's just calculate the mean of column B. So I'm not going to type it now, but that's what I would write. Calculate the mean of column B. And then step 3 would be calculate the difference between A and B. I'm typing with one hand, so I'm not writing full words now. But basically, you get the idea. So this is pseudocode. This part is pseudocode. It means I'm not actually using any code language's syntax. I'm just writing out the steps. So it's like writing a recipe. It's like you're not actually baking the cupcakes, but you are writing out when I'm going to bake cupcakes, the first things I must do. I must put the flour and the sugar together, and then I must stir in the oil. So it's like writing a recipe. So pseudocode is a recipe. So that's what you do over here. You just write for me the steps, just using normal words that you would follow to do this. You don't include the code. You're just writing to me what would you need, which steps would you need to follow to be able to get this answer, the answer of the difference in the mean of unstimulated CRP.